Unfortunately, the notes did come off very poorly off the copy machine. But this actually is the central limit theorem. Again, this book kind of doesn't throw in a few things that they probably should, that they really should be independent events, but we'll let them slide on that one, I guess, because I don't think they're really going to give us any that don't work. And so if you need to fill in any parts of your notes, feel free to do so, because this is one that you will refer to back to quite a bit, or I'm sure that you could search for it and it would come up with something very similar. So if you take some samples of size n, and we would like n to be greater than or equal to 30, if they're drawn from any population with a mean mu and standard deviation sigma, then the sampling distribution of sample means, that's huge, okay, approximates a normal distribution. The greater the sample size, the better the approximation. That's if it's any population. The second one is if the population that you start with is already normally distributed. Then that sampling distribution of sample means is normally distributed for any sample size n. N doesn't have to be bigger than 30 at that point. So if you start with something that is normally distributed, you don't really have to make n all that big. For example, the dice experiment, when I gave you 2 dice and found the sum. Was that normally distributed already or not? Yeah, what's most likely? The 7, and it tapers off from there. That is definitely a normal distribution to start with. And that's why it really didn't, I think after the first 8, we actually had a really good approximation of the mean, and it was doing very well. And then I had you keep doing it, and it really didn't affect the mean very much. Right? It stayed right about 6.95 or something like that, where the mean should have been 7. So we were very close. We are going to do eventually the simulation of what if I just give you 1 die. 1 die is not normally distributed. Remember, it's uniform. It's all 1/6, right? Probability of getting that if you just do 1 die. Okay, so we will do that one, and we will see how long does it take to actually get there. So it says in either case, meaning 1 or 2 up here, the sampling distribution of sample means, I know that's a mouthful, has a mean equal to the population mean. We talked about that yesterday. Isn't that what we did? Okay. But now it's in an actual theorem. It's being stated. And the sampling distribution of sample means, again, that's a lot, has a variance equal to 1 over n times the variance of the population, because you have to divide by n, right? But then why are we having the square root of n at the bottom of ours down there? Right, so this is variance, right? You divide by n, and I got to take the square root. So that's why there's a square root of n at the bottom. Okay. So I would say these two most important. And this is showing you what it looks like somewhat in action here. So this one right here is kind of number 1, right? This is any population. Does that population looks normally distributed to you? That's all over the place, right? And that can happen, right? I mean, that's a possibility. What they're saying is if you take, and obviously if it's not normal, you have to do n greater than 30. So you take a bunch of samples out of that population and you find the mean. You keep throwing that into that information somewhere, and then you make a distribution of just those means. And it's telling you it's going to end up looking something like this. And this right here is, I think this actually came out better on yours, didn't it? This is the standard deviation of the sample means. Standard deviation of the square root of n. Wow, that's bad. So this one here means that the mean of the sample deviations is equal to the mean. Did it really move? Here was the mean here. They tried to put them right above each other, and see how the mean didn't move? Here, one standard deviation was quite far. Here, at that part, if this is normally distributed, where should that one standard deviation be? What's this point called again? Point of inflection. What percent should be in here? 68. So do you see how that kind of tells you how far to shoot those things out? Because you know about 68% has to be in there. Can I do that for up here? Oh, this is this. Not really. Okay, it's not normally distributed. You can't do that. And look at how big that standard deviation is. This is still the mean, so you see how the mean really didn't move a whole lot. Now here is what if you start off with something that's already normally distributed. Here's your mean. And once again, there it is. Once again, there's your standard deviation of that one. Now it's the same thing here. Once again, that happens at right here. So what percent's in here? How about in here? Can you actually do it there? Yeah, you actually can say it's about 68% in there, right? And here you can say it's 68%. Okay. So the mean doesn't move. The key is, do you notice what happens to that? Yeah, this is going to make it, keep bringing it in, and it's actually going to make the little higher up, and it's going to squeeze in the sides. See how that works? And you're actually going to have a couple graphs today that I'm going to want you to do a couple different sample sizes and put the graphs all on the same axis. In fact, I think I have to go get those copies. But you should see it actually happening. Oh, what if it's 12? Oh, it's right here. What if it's 24? Oh, it's right here. What if it's 36? Oh, it's right here. And you're going to actually see it physically moving. So that's why I'm going to have you put all three on the same graph. Okay. It's very simple to apply. Phone bills for residents of Cincinnati have a mean of $64 and standard deviation of 9. So is that of a sample, or in this case, would that be population? That's of the population, right? So I could call 64 as flat out mu, right? And 9 is flat out sigma. Okay? Shown in the following graph, which I believe you have, right? Right? So it says random samples of 36 phone bills are drawn from this population, and the mean of each sample is determined. Okay. So we got 36. Can we use the central limit theorem or not? It was not normally distributed. How many samples am I taking? Is that enough, according to the central limit theorem? Is sample size 36 enough? What does it have to be? 30. So if it's not normally distributed, you need at least a sample size of 30. It's not saying how many of those samples you need, but it is saying that the sample size must be at least 36. So it took 36 phone calls. They were drawn from the population, and the mean of the sample was determined. Calculate the mean and standard error of the mean. That is what this is, standard error of the mean. Right? Oops. Then sketch the graph of the sampling. I'm going to be interested to see what you do for that one. That could be something. All right. So what am I asking you to calculate right there? It's the mean of the sample distribution is what I'm asking you to find. What should it be if I use the central limit theorem? 64, right? Should be the same. Right? The mean of that 64 of the population, this better be the same. You got to love it when I'm asking you to give me an answer that you already have. Right? It's awesome. When central limit theorem actually is going to become more powerful is when we kind of do things in reverse. That's when it's going to come really well. Now we got to find out. So what am I asking you for there? Standard deviation of that sampling distribution, okay, which happens to be of sample means. Okay, it is not 9 because the rule says right here. Do that. Take the standard deviation of the population and divide by the square root of n. So standard deviation is 9 divided by the square root of however big that sample was, which was 36. This was a nice number, okay. And your assignment, they're not so nice. Use your calculator, whatever. It's close enough, okay. The reason these are nice is obviously we know that number. It's 6, right? I'm going to give you numbers like 12, 24, stuff like that. But you know how to do that. It's not that hard. And so we came up with, this isn't even approximately, right? I mean, this is right on, 1.5, right? So wait a minute. Let's look here. Do you agree that the mean is still here? And they're saying the standard deviation is 9. So how far out is it marked on yours? I can't even see this thing. What number is that? 70, 73? Oh, so they actually just put it out there? Oh, okay. Well, that was nice of them. Can I say that's 68% in this case? No. It's probably pretty close, though, right? I mean, this isn't that bad. Right? It's probably relatively close. But we can't say that because it's not a normal distribution. We don't know. Now, over here, here's the fun part. Yeah, draw it in there. So 64 goes right here. Agreed? And how far about is that? 73 is about that far out. Right? And 55 is about that far out, right? I hope you agree our mean should be at 64. So that's going to be the tallest part of our graph here, right? But we're not going to go 9. We're only going to go 1.5. Oh boy. Okay. So we're at 1.5 each way. And so what number would this be? This would be 65.5, and this would be careful. There you go. Common thing is what, 63.5? That'd be bad, right? It's not 1.5. These have to be what? Points of inflection. Oh boy. Pretty much. Yeah, this is to your discretion at this point. But what we know, so let's say you did that, right? The mean would be up there. If I just, let me do a different color. If I bring this down, what percent has to be in there? So do I have a lot of leeway with the bottom of this thing? Not really. It can't be very wide, can it? Because that's got to be 68% in there, so I got to be very careful. I can't just start going way out here like this. I mean, you've got to be very careful. So you just do something like that, you know. That's believable at least, right? No, I don't want that. I want you to get the general idea of what's happening here. We'll do calculations later. Let's figure out this theorem first before we even try doing anything else. All right? Because let's face it, if you can't draw this graph, you really don't know what's going on. You're putting a lot of information together here. So it went from this to that. Went very wide. Because what we're doing is we're just taking a mean from the sample. That's the only bit I'm taking. I did this thing I took 36 phone bills. I found the average of those 36, and the only bit of information I took from that sample was the mean. I threw it over there. And then maybe somebody else took 36 other phone calls, or phone bills, excuse me. They took the mean of that, they threw it over there into my distribution. They threw it, and then everybody kept doing that. So the only thing we were taking was the mean. So did we do a lot of dividing to find that mean? So should the mean still stay pretty darn close to where we were? But you see, all these means are going to still be pretty close, aren't they? Maybe somebody will give me a mean of 63, right? Somebody threw that answer out there. Maybe somebody's sample gave it a 65. Somebody's sample gave it a 64. Somebody hit it on the head. Another sample gave it. Do you see how those numbers, those original phone bills, one phone bill could have been $100, right? So do you see how that standard deviation is huge of the population?
So we're talking about the population.
Cincinnati in this case.
Is that other one like the exact distribution of population?
Right. But what we're doing is we're getting it to a normal distribution so we can use our tables and use our calculators and all our powerful stuff to find out what's the probability it's greater than 80. What's the probability it's less than this? Do you really want to sit there and find areas underneath this curve? This one on the left? Those in calculus know that's probably not too fun. Look at how fun that function would be. But we're getting it to one that's normalized. So now I can say, what's the probability it's greater than 80? And we should be able to start figuring things out from that. And that's the whole idea of this, is to get it normalized.
Feels like you're like chopping off all those meetings.
Well, my graph's not perfect. But this is not, these two are not necessarily the same distribution. This is of the entire population. This is of just the sampling distribution of sample means. And we're trying to bring it in. Okay? And that should happen. But do you understand why the standard deviation is getting smaller? Okay, it's because of how we're calculating it. Okay, and let's see what I think I actually have the actual graph here. Whoops. Oops, if you actually hit the button. So we're relatively close for doing it by hand. All right. This is one we've actually talked about already this year. The white oaks. There's your distribution. Does the central limit theorem work? The big thing that was at the beginning of today.
No.
Why? What's number 2 say? Number 1 says if it is not, it's any population, it has to be bigger than 30. If the original is normally distributed, you don't have to worry about it. But again, do I know enough information about this particular normal distribution to get enough information out of it? Okay. We're working it towards the standard normal distribution, which saves a ton of time. Okay. So what's the mean here? 90. Standard deviation? 3.5. N is only 4. So you know what? That's okay. Okay, this one's very close to kind of that dice one that we did. We did sample size of 8, and it was pretty much right on right away. Okay, because it was already normally distributed. Well, it's not that it says random samples of size 4. So we took 4 of the trees and found the mean. Started over, took 4 trees, took the mean, threw that number out. Took 4 more trees, took the mean, threw it out. So we're getting a bunch of means, and we're making a distribution out of all those means. That's what a sampling distribution of sample means is. It's like I gave all of you, and I said, go pick 4 of those trees and find the average height for me. And bring that number back and that number only. Not your tallest tree. It doesn't even have to be different. It could be random trees. I say, go out and pick random trees. Don't tell anybody else which trees you picked. John goes out, he picks his 4. Oh, this height, this height, this height. One's probably going to be very big, one's going to be small, and he's going to give me the mean, and that's the only information he's going to give me. Don't give me anything else, and you all do the same thing. I'm going to take a distribution of what you gave me and just the means, and I'm going to distribute them. You know what the funny thing is the central limit theorem says it doesn't even matter. It's going to take care of itself. That's the beauty of it. Still going to work out. Because is that random? That if you went out with the purpose of picking all the tallest trees, is that random? No, it's not. That's the key. You throw this word out, and pretty much everything we've done this year, worthless. If you throw out that word, random. See, if you go out with the purpose that you know you're going to pick the 4 tallest, that's not random. Okay? It's not random if you go out with a mindset that you're going to pick the tallest. All right, so what's the mean? Oh, you got to love that. You already know the answer. All right. Now, standard deviation of those samples. Take 3.5, which is your original, and divide by the square root of 4. Oh, look at that, a nice number again. Equals basically 3.5 divided by 2, otherwise known as 1.75. I would like you to try and graph that one for me right now. Do something similar like the way we did last time. I meant to give you little axes down there that were the same length and everything, but the computer and copier were giving me enough trouble. So I figured you could handle making a line. If you really wanted to, you could have just drawn it right on the same one. I wouldn't have really cared and just drawn it right on here. You know, it would have worked. There it is again. And what was this one? 3.5. What number is this? 95 right here. Is this what that number is? Okay, so 3.5 is right about here. Does that look about where the point of inflection is? Yeah, it looks like it. Same thing over there. So here it should be just 1.5 point of inflection. Again, what has the biggest thing you want to keep in mind is what percent has to be in there, and that'll help you draw the rest of it. I mean, you can't sit here and do this, you know. That's not reasonable. And this one's what, right about there and there. Believable. Okay. So yeah, this one here, those blue ones, no good, because that's obviously not going to be 68%. Okay. Any questions on that? All right.